Good afternoon. This is CIVE 634, Surface Water Hydrology, and I'm Professor Victor Ponce from San Diego State University, Department of Civil Engineering. This is class number 072, which is the 7th week, the second lecture. There's 2 lectures per week. And the subject today is droughts. So today my plan is to cover starting from E18, 19, 20, 21, and 22. If there's time, we'll get to 23. If not, I'll assign it for you to read. 23 is just a book. It's a book on droughts. It's a good piece of material, and I'll explain to you how is it that I originated that report. It's a report, actually. It's a pretty long report, maybe 30 pages. But let's just go back first, and let's get to E18. This E18 is a paper that was published in the year 2002, written mostly by Mr. Shetty. He did all the work, and Professor Tahir Chamsi was out there from Iran in the lab, and he also collaborated, and that's me as a third author. And we also had an associate from Mexico that had helped with the data, and it is usual and customary in these kinds of scientific articles, you put everybody on site that worked on the paper. So these 4 people worked on the paper over a period of maybe 6 months. So drought characterization in the Ojos Negros region, Baja California, Mexico. Why did we get involved in this? Because at the time I had a grant. I actually had a grant from 1999 to the year 2005. I had several years of grant where we studied, our group studied in Ojos Negros, researched the valley of Ojos Negros. And I don't know, many of you may not be familiar with it, but I'm going to show you where it is. Okay, so this is the paper. This is the authors. And you'd be surprised that there's a summary in there in Portuguese. And the reason is because we published this paper in a Brazilian journal, because I had some friends out there and they wanted papers. The magazine was, the journal was a new journal, and they wanted papers, and they called me up, and I said, sure. So we sent this paper to the Brazilian journal. It's a reputable journal. One of the universities out there is supporting it. And so we published this paper. It's an index journal anyway. So it's published around the world. And everything's on the web these days. So, I mean, if you wanted to get it, you could get it readily. If you cite it properly, you can read it. At any rate, so we applied in here our conceptual model of drought characterization, which I already talked about, only that at the time I didn't explicitly talk about or detail any calculation. But in here, we're going to do the calculation. And we do it in Ojos Negros because anything that related to Ojos Negros in the water area from the year 1999 to the year 2005, which is the period, the 6-year period that we were funded, that was our job to do. So we wrote this paper on the droughts in Ojos Negros. Let's see the title, Drought Characterization. That's right. This is in Baja California. So everybody knows what drought is. What is drought? Droughts is a period of 1, 2, or more years, up to about 6 years, typically, okay, that rain is deficient. Normally, rain is a certain amount, and it is deficient. How deficient? It could be 25% deficient, which is mild drought. 50% deficient is already mid-sized drought, and 75% deficient would be a very serious drought. 75% deficient meaning if 100 units is the normal, 25 units would be 75% deficient. Okay, so we have in here the paper. We explained the Ponce model. That's my model, the one that we developed in the year 2000. Okay, the climate types are defined in terms of the ratio of mean annual precipitation to mean annual global terrestrial precipitation, which we believe is around 800 millimeters, which is about 31 inches. Okay, so we apply the methodology, and first we had to gather the data, and this is what Mr. Shetty did. Well, we had to go over there in Ensenada. there's an agency out there of the Mexican government that publishes the data or that has the data. So we went out there, and we have friends out there. So they helped us to get the data, and we got the data for several stations. However, how many, I'm not sure, but we're going to check that later. This graph that you see in their table is not a graph, it's a table. This is our conceptual model, and we have already reviewed this. It is a very interesting and fascinating model. Not that Professor Ponce developed it, but the reason I think I told you the other day was that I had experience all the way from the super arid to the superhuman. And a lot of hydrologists don't have that kind of experience. A lot of United States hydrologists, those that have not gone out of the country, well, I shouldn't say that, because I mean, the United States has everything. No, not everything. There is no tropical rainforest in the United States. However, I did mention to you, I think I did, that there's a little corner in Puerto Rico that is supposed to be tropical rainforest. But that's very small amount. But at any rate, we constructed this table based on experience, based on research with Mr. Pandy, you remember my other author, and who knew a lot. Pandy had been working for 10 years on droughts, and he knew a whole lot of information. So I relied on Pandy to back up everything that I was thinking that I could say. And we, of course, have experience. We've been around, and we realized that we could center the center of the climatic spectrum at 800 and then come down all the way to 100 in steps of 2, products of 2. So 800, 400, 200, 100, and less than 100 is less than 100, all the way to 0. Okay. And as we know, there's a spot in northern Chile where it never rains. It's called Atacama Desert. And on the other side, you could go from 800 to 1600 to 3200. 3200, by the way, is the rainfall in the central Amazon. The central Amazon, around Rio Negro, somewhere around there, Pará, is 3,200 millimeters. And then it kind of reduces to 2,500, 2,200. So the Amazon has a lot of rain, and more than rain, it has water, because it's very large basin. That's the Amazon, but it's not the wettest. The wettest is at Cherrapunji, India, in Assam, eastern India, where the precipitation, recorded precipitation mean annual, has been measured at 12,000 millimeters, which is a lot. It's extremely a lot. I've seen places in Ecuador, in southern Ecuador. No, I'm sorry, southern Colombia. Was it? No, it's southern Colombia, which is 7,100 millimeters, and that was already high. And there's a few, maybe I'm not familiar with all the data around the world, but those are the numbers that I can quote you at this time. So that's the climatic spectrum. Now, the issue from there, to moving from there to the values of evapotranspiration, that's a little tougher. But we have a lot of experience. We've handled a lot of the formulas, you know, the Penel-Monteith formula. We can run the Penel-Monteith formula and make it do whatever we want it to do. And that's a good thing with what we could do at that time. I should tell you at this time, now that I think about it, that when we did this, we didn't have the calculators, the online calculators. The first online calculator that I put together on the web was in the year 2004. It was a very simple online calculator. You know what it was? It was the conversion from Roman to Arabic. I figured that if I could do that, I could do anything. And we did it. We did it. It was interesting. Interestingly enough, and this is something kind of side topic, the Romans could only count, I learned that at the time, I didn't learn, I kind of realized, the Romans could only count to 3888 because the 3889 doesn't exist. That's fascinating, isn't it? Interesting. At that time, that's 2,000 years ago. At any rate, so they couldn't with their system get more than at that point. I guess they didn't need it at the time. The Arabic system, numeric system, I believe, originated with the Arab people, Arab culture, and then it became, established in Europe and other places. Okay, so that's evapotranspiration, and the rest of the stuff in here is all constructed based on data, everything. We looked at intensity, duration, frequency. I wanted to come up with intensity, duration, frequency for droughts because I felt that we knew everything about floods, intensity, duration, frequency, but nobody had really come out and tried to develop the intensity, duration, frequency for droughts. So that's what we did. People were talking about severity. They were talking about duration, sure. Intensity was a little bit fuzzy. There's also the issue of strength of the drought. There's all different kinds of names out there. But we said, no, we're going to do the IDF, intensity, duration, frequency. As you can see, this table is labeled intensity, duration, frequency. Because we wanted to show that we could do IDF not only for floods, but also for droughts. And you would recall that I think I have said in the last few days or weeks that up to 1989, 1990, I was a flood expert for almost 20 years, 73 to 89, so that's 16 years. And then in 1990, 91, I decided to reverse the issue and go to droughts. And then I went to Brazil in 1993. And then 8 years later, we put this conceptual model, which is kind of simple, but it is very practical. Okay, so what did we do with shedding here? We came up and analyzed the data in Ojos Negros. For your information, where is the Valley of Ojos Negros? I'm sure you guys never been there. Many of you maybe attempted to go or perhaps tried or visited Mexico, actually. Tijuana is over here. Ensenada is over here, about 100 kilometers south of Tijuana. It will take you about an hour and a half to get there. And a lot of people visit Ensenada. It's a nice town. These towns Ensenada is a nice town. But very few people venture east of Ensenada. If you do east of Ensenada, within 40 kilometers, you get to this valley, which, by the way, is a beautiful valley. It is a graben. I think the word is graben. It's a German word that means depression. It's a depression between two faults. That's a graben in German, but it came into the English language many years ago. So this is a graben. It has a geological history, very interesting, and so on and so forth. I mean, I'm not going to talk about Ojos Negros right now. There's a lot of publications out there that we have put together over the years. I should mention to you that when we started publishing Ojos Negros, we researched the literature, and we didn't have any Google at that time. But I went over to the library of the university in Ensenada and tried to figure out how many publications there were on Ojos Negros. And I found 2 at the time, 1998, 1999, when we started our research, which of course means that Ojos Negros was totally forgotten, abandoned by everybody, all the scientists. So we started putting up publications and they showed up and so on and so forth. We became popular because we basically put the Valley of Ojos Negros on the map back in the year 1999, in the year 2000. I have one of our students, Cesar Erkan from Turkey, that did a master's thesis in Ojos Negros on the climatic changes brought upon by the exploitation of groundwater, because Ojos Negros is a place where they use a lot of groundwater. Okay, so that's the story. Now you know where Ojos Negros is. If you want to go from here to Ojos Negros, it'll probably take you 3 hours. If you know what you're doing, it's about 3 hours. At any rate, so next is we looked at the various data stations, climatological data stations. How many? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 climatological stations. And the fact of the matter is that at the time we didn't have a good way of putting a map together. So it's kind of ridiculous that I should say that nowadays that we have GIS and so forth. Everybody's putting up out fancy maps, but I recognize nobody's perfect. We had a latitude, longitude of the data, and we put them on this quadrangle here, or this graph where we see the location. The Valley of Ojos Negros is right here in the middle. Okay, so we're, as far as the geography, we're fine. Okay, then we characterized the drought, and we came up with this chart over here, which since you can't see it because it was typed in the page, it was presented in the page like that. I just scanned it, not the same. No, I cut the figure and put it below so you can see it. So we have 10 stations in here. latitude, longitude, altitude over here. Valley of Ojos Negros is about 700, right? That's right. Look at this, 712. I still remember the data. 700 to 740 is Ojos Negros. 712 is the station at Ojos Negros, meters above sea level. But you have less, and you have more. This Boquilla Santa Rosa, I'm curious at this point now. Let me pull back in here a little bit. The previous page. Yeah, right. The Boquilla Santa Rosa is actually west, meaning next to the ocean, and that is why the elevation is very low. You can see the elevation of Boquilla Santa Rosa is 50 meters above sea level. That's near the ocean. Okay, so we have the mean average precipitation. Okay, how many years? This is the years of data. No, I'm sorry, I take that back. The years is this, the number of years of data. Ensenada 72, that's cool. That's the largest number. Then we have the mean annual precipitation in millimeters, of course. The number of events, drought events, the number of drought events. And then our calculation shows the average duration, intensity, and frequency. Or intensity, duration, frequency. That's usually the way we express it, like IDF, intensity, duration, frequency. So that is basically the result of this paper. And there's a few other graphs in here. For some reason, I can't grab it. Let me see if I can get over here. Okay, there we go. Now we can, over here, we're here. And then we have a few charts in here that we put together. Predicted versus computed drought. Is that good? I mean, this correlation is about 60%, maybe 70%. But that's okay, because all conceptual models are not supposed to be perfect. There are concepts to work on. The first cut, they're not supposed to be perfect. Besides, I don't think anybody can predict a drought these days. You cannot. I think I already talked about that. Droughts are difficult to predict. You expect something, it doesn't come. Remember, we talked about the drought in the Paraguay, the upper Paraguay before, extensively, by the way. So these are considered to be good. They're considered to be okay, these graphs. And I finalize in here with references to Professor Dracup from Berkeley and UCLA, and our own papers by Ponce and Pandey, and Mr. Sharma from India. I believe that's an Indian name, if I know one. So that's it. That's basically the paper that we put together with the three gentlemen that were my associates at the time. This was the year 2002. Mr. Shetty worked all 2002 for me over in the lab. Well, he was assigned, I actually was paying. He was under my salary because I had research contracts there at the time. Okay, so now I'm going to delight you with a video of the place so you can see it. And then there's a good story at the end, okay? So let's take a look. That's the Valley of Ojos Negros. There's a fault on the hill and a fault on the hill in front of us. There's two faults.
In 2002, I published a paper on the subject of drought characterization in the Ojos Negros Valley.
That's it. That's the paper we just reviewed.
In Baja California, Mexico.
And that's the town of Ojos Negros. That town you see in there, the town of Ojos Negros. I'm not sure how many people, maybe 5,000. I'm not 100% sure of that figure, by the way.
California, Mexico. A.V. Shetty, one of my co-authors, had performed a detailed statistical analysis of the data for 10 climatological stations in the vicinity of the valley, located 25 miles east of Ensenada.
How did I ever get to that place? Well, I can go back and say that in 1990, when was it? The 1991, I attended a meeting in Ensenada. It was a hydraulic meeting, civil engineering, hydrology meeting. And I met this lady, one of the professors out there. And she introduced me to one of the students at the university who wanted to do a thesis. And she advised that I should cooperate or collaborate with them. And so I did. So that's when I started my involvement with the Ensenada University. That's actually the University of Baja California in Ensenada. And one thing led to another, and pretty soon we were researching the various valleys in the area because the gentleman that was doing the thesis was going to be doing a study of the hydrology of the valleys in the region. So that's how we got to the place. Several years later, by the way.
The results show that the average frequency of droughts in the region was 3.96. That is,
A calculation, a detailed calculation showed that the frequency was 396, the average of all the frequencies.
that droughts recurred in the valley approximately every 4 years. Afterwards, we followed up with a visit to the valley, where we met the longtime owner of the Ojos Negros Ranch. I struck up a conversation with him and asked him what was the frequency of droughts in the valley. Without blinking an eye, he said, every 4 years. He was right, and he did not have to calculate it.
He knew it. He had lived there for 30, 40 years, and he knew that every 4 years, on the average, the drought was going to come back. And not uncommon for this type of weather, by the way. Okay, so next is our paper on the management of floods and droughts in the semi-arid Brazilian Northeast. You recall I did explain or detail how I got involved in droughts. I said 1990, after I had looked at baseflow, I said while I was doing it and after I finished the baseflow study in 1991, I decided that I wanted to do droughts because I didn't want people to say, oh, Ponce, the only thing he knows is floods. I said, no, I'm going to study droughts, so that just to put a monkey wrench on that statement. So I was interested in droughts, and in 1993, I had a chance to do a sabbatical. What is a sabbatical? A sabbatical is a privilege that faculty at American universities have every seventh year, or 6 years of teaching, the 7th year, you can apply for a sabbatical. Sabbatical, they call it a sabbatical year, but it's not a year, it's half a year. There is some universities that are, I guess you could say they have resources, give their faculty full year sabbaticals. California State University doesn't do that. And I don't think many other universities in the US, I could be wrong on this, they give you half a year, which is fine. People take it, I took it. I've taken the sabbatical 5 times, no, that's right, 5 times in my 40-year career. Okay, the second time was this one. I said, I'm going to study droughts. Where should I go? Turned out that I researched the issue, and Brazil had a very important agency in a place, in a localized geographical area, which they referred to for the last 100 years as the Drought Polygon. I repeat, the Drought Polygon. The polygon meaning it's a polygon, many sides, various states, 4 or 5 states, where droughts recur. So I said, this is the place I'm going to go. So I went over there, and typically the sabbatical gives you for 4 months. So you don't need to spend the 4 months on the site. So I went over there for a couple months. Then I came back and wrote this paper based on all the information that I had gathered while I was there. I was there in middle of August to middle of October, and then I came back and finalized this paper. By the end of December, it was done. And luckily, it was at that time that there was a magazine that had opened up a special issue. And the issue was, the Soil and Water Conservation, magazine of Soil and Water Conservation had opened up a special issue, and they were inviting people to submit papers. And I had some friends out there. It's good to have friends, you know. I had some friends, people knew me. So I submitted this paper and it got published. They told me basically the paper was going to get published no matter what, because they really wanted papers and so forth. The point is that we published this paper in a recognized journal, the Journal of Soil and Water Conservation in the United States, in a special issue of the journal. So that's this paper called Management of Floods and Droughts in the Semi-Arid Brazilian Northeast, the case for conservation. I went over there with an open mind. I was going to study droughts. Whatever droughts meant, I was going to try to research it. And so I did. But interestingly, though, by that time, 1993, I had already become, I guess, what amounts to some sort of an environmentalist. I had been a straight civil engineer for almost 20 years. And I felt at the time, because of my involvement with Pacific Gas and Electric, and the view of base flow is an important subject, I realized that there was a lot of things that I didn't know at the time. Among them, well, I didn't know about droughts. Droughts is totally different than floods, totally different. But not just that, I didn't know about ecosystems. I didn't know about water relationship with biota, a lot of things that I needed to learn. So I said, I'm going to go over there, get in the library, because I had experience in the Library of India, of the National Institute of Hydrology in India. And I had learned a lot. I discovered Buddhiko in India, as a matter of fact, 2 or 3 years earlier, 1991, this was 1993, so 2 years earlier. So I said, I'm going to go out there and hit the library. Remember, 1993, there was no web. For your information, in case you don't know, our friend Tim Berners-Lee spent 5 years, 1989 to 1993, working on the World Wide Web. And in 1993, he put it out. And interestingly, he, being Tim Berners-Lee, decided to give it out for free to the entire world. He was a real nice guy. And he claimed that he only put 1% of the whole thing. The other 99% he had taken from many other people starting 100 years ago, which is, by the way, correct. All you do is you add a little bit at the top of the pie. So that's what he did. He gave us the WWW, the World Wide Web. It was a good name, by the way, in 1993, somewhere in 1993. And I happen to know because San Diego State is a very active university. We claim to be, well, I don't know what I'm going to say there. We claim to, but we are good. We're good. I think we're good. You guys are at a good school, good California school. And in 1994, the computer center people, the computer guys, were moving around talking about the web this, the web that. And I didn't know anything. And of course, it took me a while to realize that that was important. I was looking at, watching it. I had friends out there, acquaintances, they were talking about it. I had my, there was a gentleman out there that was helping me out with the computers. You know, we always, engineers, civil engineers don't do IT. If we did IT, we'll be hired as IT people, and then we would encroach upon the work of other people. That is not done. We're busy with our civil engineering, with hydrology, with hydraulics. So we always have to rely, whether we like it or not, on IT people that are going to help us get rid of the problems that normally pop up in the computer work. So suffice it to say that it took me 4 or 5 years to get on top of it. By 1999, I had realized that this was the big thing. It wasn't going to go away. I thought it was going to go away. No, it's not going to go away. It's good. Remember, I'm talking as a person that is all of a sudden encountered or confronted with some new technology. And don't forget that at the time I was already 50 years old. And I don't want to get into details, but 30 years old is the peak of your potential. I was already not at the peak of my potential. But at any rate, long story made short, I endorsed and I joined the web in 1999. So I've been on the web for 24 years now. And the record shows the extent of my website. Because at that time we started putting the web and we have not ceased. Every day we add something. That's why it's big. Okay, so the paper I titled Management of Droughts and Floods in the Semi-Arid Brazilian Northeast. I came about to the realization at that point, there was something about a cybernetic mechanism. You heard me talk about this before, that floods were followed by droughts and droughts were followed by floods. And I said to myself, this is interesting. I know, at the time I knew that the world was cybernetic. And interestingly, why would I know that? I'm a civil engineer. I'm not supposed to know all those things. But I actually lucked out because I read the book by Vice President Al Gore. Vice President Al Gore wrote a book, The Earth and the Balance, 1991. And that led Bill Clinton to pick him as his VP. And I believe, if I'm correct, Bill Clinton picked Al Gore because he read the book, which I also read at the time it was published. And he thought Al Gore was good, a good partner, because Bill Clinton didn't know a whole lot about environmentalism or environmental action. And he thought that, that Al Gore would be a good partner in this area, which he was, okay? The rest is history. I'm not going to speak any more about Al Gore. He doesn't have, for one reason, not a good reputation, but he's a good guy. So at any rate, having worked with or read the Al Gore book, he has a lot of things in there that they really opened my eyes. Al Gore is not a scientist. He's a media guy. He's a newspaper guy, but he knows how to write, and he writes about the right things. That's important. He's very smart. He did say at the time, by the way, you guys maybe don't know this, but he did say at the time in that book that he hoped, or he expressed it in that way. He said, we're hoping that by 2025, we, meaning society, will get rid of the internal combustion engine. He said that. And that was some statement to make at that time, because we're looking at the future, and the future cannot be guessed. California, the state of California, leading the US and leading the world, is going to get rid of the internal combustion engine by 2030 by legislation. So Gore missed by 5 years, extrapolating into the future. Is that good or not? It's excellent in my opinion, okay? So this is the preface to the paper. This paper deals with droughts from the Brazilian standpoint. And since they have a lot of experience, then it's good as a case study for us to take a look at what they did. Furthermore, the Brazilians concentrated in this area because they call it the Drought Polygon. And why is it the Drought Polygon? Because it's a polygon. You can see in there, right there. It's got a bunch of sides in there. Several states are in the Drought Polygon. Not the coast, because the coast has the exposure to the ocean, so it rains over here. But then all of a sudden it dries out. So the state of Ceará, 90% of it is arid. Paraíba, almost 90% also, a little bit more than 90%. Pernambuco, sure. Bahia, they call it Bahia, same thing. Piauí also kind of drought related. Now, interestingly enough, though, there is a gradient over here, a humidity gradient. Here, it's very wet. Then it all of a sudden it's dry, all of a sudden here, and then it starts getting wetter again. Piauí, for instance, is dry, but it is also wet. Bahia depends on where you are. So at any rate, long story is that this is the Drought Polygon of Brazil. What they call Drought Polygon, because over the last 100 years, since Brazil has been an independent country, Brazil was one of the last countries in Latin America, certainly in Latin America, and in America too. I mean, North Americans. Brazil became independent in the year 1889. United States, 1776. Peru, 1821, and so on and so forth. So Brazil was the last one. Why were the last ones? Because they were governed by the Portuguese, and somehow they didn't get around to whatever it was. I'm not privy to the information why they were late, but they were kind of late in the issue of becoming independent from the Europeans, from the European countries. Okay, so they were late. So turn of the century, now 1900, they were only 11 years into being a republic. And then all of a sudden they're hit by all these droughts. Where? In the drought polygon, because Brazil is wet. If you have a drought in the Amazon, it occurs every 100 years and nobody notices it. Who cares? I mean, you don't live 100 years, so you have ample time not to even sense it, okay? So there are not a whole lot of droughts in the Amazon. And we talked about that in other places. But this place, recurrent droughts and intense droughts, severe droughts. So that's why they call it the drought polygon, and they put in place policies in order to control it or regulate it or manage it. Manage is the better word. So the drought of the Brazilian Northeast, historical perspective. Interestingly, though, the record of the United States is about, when we studied Arizona in the year 1983, the record of the Santa Cruz River was 80 years at the time. That meaning Arizona had 80 years of record, the rivers of Arizona. But in Brazil, the record goes all the way to 1600. Look at this, 1600, 1600. Why? Because the Portuguese were out there already for 400 years. The Portuguese arrived there in the year, say, 1570, 1580. So they had a lot of time to record the events and so forth. So there's a lot of data going back 400-500 years in Brazil about the droughts and the floods. Floods and droughts, they go hand in hand. But in here, the droughts are more important because they're intense and there was a lot of problems in there in the past. There was a lot of famine and so forth. Pretty bad things that happened because of the drought. As a matter of fact, it says in there, the drought of 1877-79, which killed more than 500,000 people. How do you get a drought to kill 500,000 people? I don't know. I'm just telling you what has been referred in the literature. Okay, 500,000 people. Okay, in 1909, the Brazilian government established the Inspectoria de Obras contra Secas, which means Inspector of Public Works Against Droughts. And they've been changing every 20, 30 years, depending on the politics, the agencies that are in charge of coming up with the management of the droughts. The first thing they did, by the way, is they said, well, what we need to do is store water. And that is very important to realize that that's the first thing that it's called upon. We don't have any water. What are we going to do? We're going to store water. So let's build dams. So they decided and they put together a program to build dams. And that is fine. There's nothing wrong with that. The problem is that, in our opinion, which is written in this paper, don't just build dams because maybe you're cutting yourself on the foot. What you should do is find out why is it that you're cutting yourself on the foot and stop it, and then maybe also build the dams like a safety factor, but not just building the dams, because rainfall could be drying all over the place and you build the dams to collect what? That's the point that we're making in this paper. If precipitation is decreasing, no matter how many dams you have, you're not going to fix the problem of fighting the drought. Could precipitation be decreasing? And the answer is yes. There's such a thing called desertification. You could dry an area. And how do you dry an area? Messing with the vegetation. You dry an area messing with the vegetation, cutting down the trees and so forth. Why? Because you change the albedo. It takes some time, maybe 10, 20, 30 years, but it does come back to haunt you. So the vegetation should be left intact or minimize the changes. That's what we should do. So that entails what we call conservation management. Not just building the dams, but conserving a management of the ecosystem conservation. That's what it is. So the story of the droughts was not put together, as far as I know. So I decided to tell the story of the droughts in Brazil. And I think we did a very good job. Current scenario. What is the current scenario? The current scenario as 1995, when we published this paper. You see Journal of Soil and Water Conservation right there at the bottom. For past 100 years, combating droughts has been accomplished by surface water storage. For the past 100 years, 1895 to 1995. The reliance of surface reservoirs have been referred to as the Asude Policy. Asude in Portuguese means build dams. Okay, so that is characterized as we're going to solve the drought problem by building more dams because you're going to store more water. Okay, so that's one of the things that was going on at the time. And then I quote, of course, my favorite scientist, Humboldt. You heard me talk about Humboldt already in his personal narrative. He had observed, we already discussed this. I believe we discussed it not in this class, but in the other class. At any rate, many of you, I think 6 of you are in the other class anyway. So if you heard it already, it's a repetition. But this statement in here is a very good statement that Alexander von Humboldt wrote in 1821. He was in South America from 1799 to 1804. And then he went back, and it took him 15 years to write the 7-volume book. I don't blame him. It's a 7-volume encyclopedia of the time, by the way. Excellent book, by the way. But dated, for sure, dated. I would say that at least 50, if not 70% of what Humboldt said at that time has been superseded. And no blame to him. He was the last of the interdisciplinary people. He had to know everything. From there, people started concentrating, and now we know a whole lot about so little you would not believe. The specialists, right? That's the story of development of the last couple 100 years. We could not have done it in any other way because our minds have a certain limit. The brain has a certain limit. You can't handle all knowledge of all. I don't need to tell you that, you already know it. Okay, climate, vegetation, and the impact of human activity. So I zeroed in here on the issue of albedo. And I was lucky to find a couple of books by a German botanist and some other gentlemen that were very illuminating. Those were some of the first biological or botanical reports or books that I read, the first. So they really made a big impression on me at the time, because they were saying the same things or talking about the same things, but from a different outlook, completely different outlook that I had never been exposed to. So I took it like a sponge at the time. I read those books 2 or 3 times. Evaporation versus evapotranspiration, we already know that. We can skip that. We're gonna have to hurry up here pretty soon, otherwise we're not gonna finish. And we have here a model of how we compare the unmet potential for evaporation or evapotranspiration in an arid region. This is what it is, and the rest is unmet. You can't meet the potential because there's no water there. It dried out completely. And on the other hand, there's no unmet potential. On the right side, every iota that could be evaporated, it is evaporated. So we move on to the next page. This is a fascinating and interesting chart. Not chart, it's a table. Why? Because it describes the mean annual rainfall and evaporation rainfall ratios in several ecological regions of the Brazilian Northeast. Turns out that the Brazilian polygon of drought is an actual laboratory. It can be considered a laboratory because the vegetation in that place has a way of gradually varying from one type to another, depending on the evaporation rainfall ratio. And for those so-called Cerrido, and allow me a little bit of Portuguese in here because these, I did not want to change the names, otherwise I would have messed it up. On the so-called Cerrido, okay, which is extremely dry, I would say millimeter precipitation, maybe 100 millimeters, almost the border between super arid and hyper arid, which is at a place called Quixeramobim, Ceará, the state of Ceará. Okay, the rainfall was 497, evaporation ratio 5.8, and as you can see, gradually decreases. The evaporation ratio increases 4, 3, 3, 2, 2, 1, 0. Very good, almost calibrated. It's almost a straight line. And over here, it goes from 497, which is kind of low, in the border between arid and semi-arid, and it keeps going up a little bit here and there. This is a typo in here. It's their typo, by the way, from Brazilian journal. This really should read, I believe the 942 should be in here and the 1.3 should be in there. I mean, you can discern that just by looking at the data. It is unfortunate that that happened, but it did happen. I believe when we translated this into HTML, we did make that change. Okay, so let me move on in here and try to get done. We made a case for conservation management. We said that you can't just build dams. You have to conserve whatever is there. Don't dry it out, because if you dry it out, the rain will disappear and your dams will be left empty. And I think that makes a lot of sense, and it has made a lot of sense. And that's what they're trying to do right now, as a matter of fact. They're no longer concentrating on the straight structural approach. No longer. I don't believe that we're doing that anymore. Not even the Army Corps is doing that. In 1993, after the flood of 1993, the Army Corps decided to rehash everything that they're doing. And they had a model, a scale model of the Mississippi at Vicksburg, in the lab at Vicksburg. Since I have not been to the lab at Vicksburg, I've been to Vicksburg once, but I somehow didn't go to the lab. Since I had not been to the lab at Vicksburg, I really could not tell you. But the point is that in 1993, the reference that I have is that they decided to retire the model because they felt that the model wasn't telling them anything that they should know, because everything was failing. 73, almost the old river control structure almost failed. 93, they had to fail the levees at 200 points, meaning the levees were not being used. They had to, in order not to lose the entire structure, they had to operate 200 levee fuses. Interesting. And one of the questions on the assignment, by the way, I think today is due tonight, is about that subject. Okay, so let's move on in here. There's 3 case studies in here: Amazon Basin, Upper Paraguay, because I was very familiar with the Upper Paraguay, and 3, the soil and water conservation with Brazil's national program of micro basins. That was interesting. I found it in a magazine, and what's interesting about this is that I'm going to read this because it's extremely important. Other examples such as that of Tupaci in Western Paraná, Paraná is one of the states in Brazil, shows that conservation management works by improving water retention, which is at the same time reducing erosion. Agricultural credits were tied to the construction of terraces. We know about terraces and sedimentation, and farmers support quickly ensued. Listen to this statement. The land is now able to sustain 100 millimeters of rainfall, 150 millimeters, that's a lot, in a few hours without surface runoff, meaning they're holding it. They have structures, very small, minute structures, micro relief, so to speak, and they're holding the entire runoff. 150 millimeters is a lot of rainfall. Okay, so we designed a blueprint in here. I'm going to finish in here, otherwise I won't have time. We put in the conservation management. The first thing you should do is conserve management. Second, xerophytic silviculture and agriculture. Xerophytic means don't use too much water. Don't use crops that use a lot of water, like alfalfa and things like that. Use something that is in tune with the environment, with the ecosystem. Surface water storage, yes, you gotta store some water, just in case. Subsurface water use and interbasin water transfer. At the time, I put in there subsurface water use, but right now I would put a caveat in there. I would say judiciously, because a lot of people around the world are using subsurface water storage not judiciously. They're actually exploiting it to the hilt. I think I did mention that the state of California, the Central Valley of California, is losing 3 centimeters per year, I believe. That's studies of the University of California, Davis, 3 centimeters per year. Given the fact that the Central Valley is extremely big, it occupies maybe 30–40% of the entire state of California, that's a lot of water. And yet we're pumping it. We're pumping it because we have to pump it. There's just too many people out there that live off that water. And we're not going to go out there and tell them you shouldn't be pumping the water. It's a tough political issue to discuss. And finally, interbasin water transfer. I am led to believe that the Brazilians are actually going to do interbasin water transfer. That is an area which is generally dry, and it is surrounded by very wet areas, only that it's expensive. You're talking in the millions and even billions of dollars to do water transfer. Right now, because things have gotten expensive over the last few years, you know. Okay, so that's the end of this. Now And with this, I'm going to move on to the next subject, the 800 millimeter isohyet health and hope. The 800 millimeter isohyet health and hope. How did I originate this idea? Well, I had it in my mind for several years. I would say beginning in the year 2005, 2010. We were doing a lot of work. In those years were some of our more productive years, both research as well as consulting, by the way. We had the project to do the La Calzada Dam in Peru. We did this and we did that. We had finished Ojos Negros already in the year 2005, and so on and so forth. And in the year 2012, I believe it was 2012. I was invited to a meeting in Tijuana, and I met over there with an architect who was one of the better architects in terms of reputation in Tijuana. By the way, he's a good friend. A friend of a friend. I have some friends in Tijuana. At any rate, so I was talking to him, and I popped up the issue of the 800 millimeter isohyet. I don't know why I did it, but it was one of my topics at the time. And he looked at me and he says, "Ponce, I never heard of that." And I realized at the time that yes, he never heard of it because it has never been written. I was just talking. I talk a lot. I said, "Oh, really? That's right. You are correct. I'm going to have to write that." So I went back, and in the next couple of days, I produced this paper that you see in here. Couple, 3 days thinking about it, because it is correct and it is the right thing. Only that he was correct in saying he was an architect anyway. He's not supposed to know hydrology. He should be informed about it, not necessarily to know. You know, I have a theory that says that education is like the calla lily. You know, the calla lily, the flower that opens up on top and then it comes down like this. So you should know a whole lot about a whole little, and a whole little about a whole lot. Otherwise, you can't function in society. Because if you only know a whole lot about a whole little, you're blind as far as everybody else. You can't relate to, and you're probably going to make a mistake. And God forbid that you have power or influence, because then there's going to be mistakes done. So people should know, should be generalist in the sense that you could without being a jack of all trades, right? But you also have to be a specialist, because you got to feed yourself. And you're not going to feed yourself by just talking about in general about things, but you must know what other people have done and what's the value of their work. So that's why I call the calla lily model of education. Okay, so let's talk about here the 800 millimeter. Let's review this. I have a vector, no, I'm sorry, a raster, but it's an old video. We may have the time, I don't know, we'll see. Living matter is made out of 3 major elements. This, by the way, this paper is very carefully written. It is extremely important. So I want you to read it 2 or 3 times before the exam. Living matter is made out of 3 major elements: hydrogen, oxygen, and carbon. These constitute more than 98% by weight of all living matter. So the biosphere is mostly hydrogen, oxygen, and carbon. 3 other elements, nitrogen, phosphorus, and sulfur, are regarded as the leading nutrients. And the acronym is NCHOPS, N for nitrogen, CHO for the 3, and PS for phosphorus and sulfur. Those are the 6 major elements of the biosphere. The first 3 are the structure, and the other 3 are the important nutrients, okay, the leading nutrients. What are the other nutrients? Because the biosphere is not just made out of those 6. It has actually 25. We can list them out: sodium, calcium, potassium, magnesium. These are the leading nutrients. Then iron, zinc, aluminum, boron, chloride, chromium, cobalt, copper, fluoride, manganese, molybdenum, selenium. Our bodies, depending on who we are, animals, whatever, different types of animals have different needs for these nutrients, but we need all of them in minute quantities, in trace quantities or whatever, but we need all of them. Lack of one of them, excessive or not enough quantities in trace elements of these, could lead to illnesses and death, by the way. Selenium, for instance, is an interesting nutrient. A trace element is needed, but if you ingest selenium too much, it'll kill you. Simply put, will start doing all sorts of havoc in your body. And that has been demonstrated, by the way, not with animals. I'm sorry, not with people, but with animals. In the issue of what happened in the north in Kesterton Reservoir. You can Google it. If you're not informed, Google Kesterton Reservoir and see what happened 20 years ago, roughly. Architecture of the biosphere requires specific quantities of these nutrients. The nutrients vary with type. Different people, different animals have different nutrients, different plants have different nutrients. Plants obtain their carbon and oxygen from the air and their hydrogen from water in the surrounding environment. Extra oxygen in water is released to the air. So you get the water, the plants get the water, they take the hydrogen and they release the oxygen. So a plant is pumping oxygen to the air. Plants must produce oxygen as a byproduct. Plants get the nutrients from the surrounding soil and, notice this, increasing in developed societies by artificial fertilization. In other words, if we didn't fertilize, we couldn't produce. Luckily, for the last 100 years, 120 years actually, we have been fertilizing. Artificial fertilization has allowed us to produce crops. I just added some fertilizer to my lemon tree, and I hope in about 6 months I'm going to have a byproduct of that work and cost. By the way, you got to go out there and buy the fertilizer. Okay, so plants require solar energy, carbon dioxide from the air, water from the supply of water in the atmosphere, and the nutrients which are there somewhere. The nutrients are the most mysterious because we really can't get into the microbiology and see which nutrients and so forth. We just have to eat well, meaning eat a diverse quantity of vegetables and so forth. Common sense says that you should eat, if you eat vegetables, you should eat vegetables of different colors because the color is related to the content. And the content, if you have a lot of vegetables, green, red, yellow, brown, etc., then you'll have a diversity of nutrients and hopefully better as far as your body's need for nutrients. So the limiting factors, the supply of solar energy varies with latitude. Plants in tropical and temperate regions are able to get their energy needs during the day or during the growing season. Carbon dioxide exists in the air in concentration that are sufficient for plants to avail themselves of as much carbon as needed. What? Carbon dioxide in the air? Is that used by the plants? Yes. But we are adding carbon dioxide to the air. We've been doing that for the last 50 years extensively in large amounts. We went up in the year 1990. The number was 358. In the year 2022, 32 years later, the number is 418. So 30% in the last 32 years. That is huge. I mean, that is amazing. That's what we call global warming. Therefore, limiting factors are always water and nutrients. Because the sun, you can't control it. You live in the tropics or you live in the poles. If you live in the poles, you don't have any sun. You just have sun, very little of it, because it doesn't get you. You know, remember, the world is round. Okay, water is limited in regions with little or no rain. Nutrients are limited in regions with too much rain. Yes, because the Amazon is poor in nutrients. You cannot grow many crops in the Amazon. That has been demonstrated. Why? Because you need the nutrients. Why don't you add the nutrients and forget about it, like you would in other places? Well, no, it doesn't work, because in the Amazon, it rains every afternoon. So you add the nutrients, and the nutrients go into the river, and then they eutrophy the downstream river. They mess it up. They enrich artificially because you added the nutrients. So that cannot be done. By the way, that happened in the United States and many other places. That's called eutrophication, the artificial enrichment with nutrients because of agriculture of the neighboring rivers. There's another problem, but that's a different problem. Okay, at the extremes of the climatic spectrum, regions with mean annual precipitation of less than 100 millimeters are referred to as super-arid. Regions with more than 6,400 millimeters are referred to as superhuman. So we have in here a picture of the Amazon rainforest, which I'm sure you already recognize, okay? But over the past 100 years, roughly, Humans have endeavored to challenge nature design by irrigating arid lands. And California is an example. The entire valley, Central Valley is irrigated. Yeah, because we felt that we could bring the water and irrigate it, and that's fact. This is a picture of Welton, Arizona. Welton was irrigation. Welton Mohawk irrigation was started in 1940s, 1950, very successful in terms of productivity, but they have to drain the water into the Colorado River, and they end up sending it to Mexico. And the salinity has increased because all the salt from Welton is going into the Colorado River. The Colorado River increased from 700 ppm to 800 ppm, about 10%, 8%. That's an environmental effect, and I'm not going to get into that story because it's too long. It will take an hour to explain to you all the ins and outs. The Amazon rainforest, superhumid regions such as this place over here, is the central Amazon, remains largely unexploited by humans because most people are uncomfortable in the high humidity that prevails in these regions. This is actually inhabited by natives. In Brazil, natives. How many so-called quote-unquote natives are in Brazil? About 1.5 million, by the way. There are in a couple of reservations out there. The Xingu Reservation in the center of Pará State has about 1 million of these people that are referred to as natives, okay? Brazilian natives. Peru also had them, but Peru doesn't have 1 million. Peru's got maybe 100,000 and spread out all over Peru. In Brazil, they're all concentrated. That's interesting. I'm not going to get in there because I would spend another hour talking about it. Let's finish here. The quandary of civilization. How to cope with the natural distribution? By all accounts, the import of water solves the problem of water supply. But this is necessarily at the cost of creating a problem of salt disposal. There's always going to be salt disposal. I read an article today on the Salton Sea. The state of California, the people of the state of California cannot agree, and I think will not agree, as to how to solve the problem of the Salton Sea. I don't think so. They've been talking about it for 40 years. I mean, more than 40 years. 40 years is the number of 1997 is when I found out. So it's 23, 26 years, 25 years. They've been talking about how to fix it, and somebody says this, somebody says that. They can't fix it. It's impossible to fix. It costs too much. And no matter what you do to fix it, you always affect somebody. There can be no solution that is not going to affect somebody. So therefore, it's not going to be done. Right now, laissez-faire, right? They're still filling up the Salton Sea with agricultural drainage from the Imperial Valley. They cannot withdraw that. If they withdraw that, the Imperial Valley goes down the drain. Now, the Imperial Valley will go down the drain, but it will take a slow process, maybe 30, 50 years, until the competitors come in and take it over. I already told you about that. Lithium is one, and the other one is the wind turbines. The wind turbines and lithium are going to eventually beat the Imperial Valley to exhaustion, and they're going to disappear. I'd say maybe 30, 50 years. I could be wrong, like Gore. I don't know, but I think 30 to 50 years is very appropriate. Okay, so the 800 millimeter isohyet, that's in the middle. So in the middle, you are not short of water. There's enough water in there, and there's also not too many nutrients. There's enough drainage, and there's still some nutrients at 800 millimeters isohyet. So you can do agriculture reasonably, okay? If you're not too greedy, you don't have to do a lot of fertilization, and yet you can still function because there are nutrients in the 800 millimeter scope. The nutrients start to disappear when you get to 1600, 2400. By the time you get to the Amazon, there are hardly any nutrients out there. It's all been washed out and lixiviated by the flow over times immemorial, like 1,000, 1,000,000 years, right? So that's the story. Why did nature put it together like that? That's just the way it works. We need to understand that that's the way it works. And that's why we're here explaining it, okay? To reiterate, if humid regions leach soils excessively and arid regions conserve nutrients due to lack of use, then the 800 millimeter region must be at the optimum balance between water and nutrients. Enough water and nutrients in quantity and quality to satisfy the basic needs of the ecosystem. Basic needs of the ecosystem, including us. it may not produce a whole lot. So if you want to produce a whole lot, you got to go to the desert, but then you got to pay for the salt. And right now, the people in Imperial Valley have been operating the Imperial Valley for 120 years, and they have not paid for the disposal. They would have to. They should, but they don't. Now, if they had to pay for the disposal, if there was a law that says, hey, you guys are producing all this stuff, you're going to pay for the disposal. Well, first of all, it's late. It's 4 generations afterwards, right? But at any rate, they had to pay for the disposal. What they needed to do was to increase the cost of the stuff they're selling, which is food and fiber. So we would eventually have to pay for it. They're not going to pay. They're just going to pass the cost to the consumer. And we are the consumers. And right now we're getting all this stuff cheap, relatively cheap, because they're not paying for the salt disposal. And that's why the salt has collected over there for 120 years. Is this the only place? No, it's not the only place. It happens everywhere. Only that the Salton Sea is the worst, meaning the biggest, the one that has more fanfare, meaning there's a lot of noise about it. Other places also accumulate salt and they put it together, perhaps hiding it, perhaps putting it in the ocean, or perhaps accumulating here and there. But they're smaller operations. The Salton Sea is a big operation. I've actually visited Imperial Valley, Imperial Irrigation District several times, 3 or 4 times over the course of 20 years. They are a big operation. They claim, or they have claimed, to be the best in arid land irrigation. The best, of course, yeah, but they're not paying for the disposal. If they pay for the disposal, God knows what could happen. Okay, so at any rate, outlook: a plentiful supply of diverse nutrients is apt to enhance biotic potential. Biotic potential is the business of life. Barring external subsidies, 800 millimeter isohyet is where life, particularly for humans, is likely to be optimal. Barring external subsidies, what does that mean? It means that we live in a subsidized society. If we didn't have any subsidies, then it would be hard, right? So therefore, if we don't have any subsidies, the 800 millimeter should be okay because it's in the middle. It's the best of both worlds. Therefore, it is where health and hope, essential to body and soul, ought to be most naturally at their peak. Because physical health is not mental health. And mental health is related to hope. If you don't have hope, you don't have any mental health. Okay, so that's why I say health and hope ought to be most naturally at their peak. So now I have in here a video, which I am going to show briefly because we don't have the time. And I'm also going to assign for you to read briefly E23. I didn't get there, particularly the last section. The last section, it says impacts, characteristics, drought mitigation, strategies for the Ojos Negros Valley. I want you to read this section. What we said at the time that they should do in order to control droughts. Okay, but at this point, I'm going to finish with just getting this thing started over here to warm up. It is a 9-minute video, so we're only going to be able to see 5 minutes or 4 minutes. Let's say 5.
Living matter is made out of 3 major elements: hydrogen, oxygen, and carbon.
Professor Ponce in the year 2011, I think. That's 11 years ago.
These constitute more than 98% by weight of all living matter. 3 other elements, nitrogen, phosphorus, and sulfur, are regarded as leading nutrients due to their importance in life processes. Among the remaining nutrients are sodium, calcium, potassium, magnesium, iron, zinc, aluminum, boron, chloride, chromium, cobalt, copper, fluoride, manganese, molybdenum, and selenium. The architecture of the biosphere requires specific quantities of these nutrients. The quantities vary with the type of organism. Plants obtain their carbon and oxygen from the air and their hydrogen from water in the surrounding environment. The extra oxygen...
Since we have already said this, I'm going to skip a little bit of it. with your
A
permission.
region with about 800 millimeters of mean annual precipitation ought to be in natural balance, theoretically with no pressing need for extra water or nutrients. If subsidies means extra energy expenditures, and if energy expenditures translate into an augmented carbon footprint, it is readily.
By the way, there's a place in India, which is in the middle of India, that has 800 millimeters. It's right. The 800 millimeter isohyet in India is coming from north to south, right in the middle, right in the smack middle. And that's where the agriculture is best. They don't have to put a lot of fertilization. They have enough water and here and there, and the products are good. Because I should tell you that when the nutrients are right, the products are good. If the nutrients are not right, the products are still there, but they're not that good.
Seen that the 800 millimeter isohyet region adheres to the principle of sustainability. We conclude that the 800 millimeter isohyet is a region where life, particularly human life, would find itself in its most comfortable and secure position. To reiterate, if humid regions leach soils excessively and arid regions conserve nutrients due to lack of use, then the 800 millimeter region must be at an optimum balance between water and nutrients. Enough water and nutrients in quantity and type to satisfy the basic needs of the ecosystem.
Where is the 800 millimeter isohyet in California? That's an interesting question. It's around San Francisco. Now, people like San Francisco, right? It's not too dry. It's not too warm. I mean, not too wet. That's why they like San Francisco. If you move north, you get too wet. It's sticky and lots of bugs and stuff. If you go south, you can come to LA, you can go to San Diego, but you got to wrestle with the water, right? And I think you must know that the water in San Diego is not that great, and we got to treat it at the tap. Otherwise, it's not good, okay? So there's a lot of things, a few things that we have to live with here in San Diego and Los Angeles that the people in San Francisco don't have to, because they are in the middle of the climatic spectrum.
In pristine soils, the type of nutrients depends on the local geology and geomorphology. For any one region, this amounts to the proverbial luck of the draw. Either we have certain nutrients or we don't. Nevertheless, once a supply of nutrients is determined by a region's geology, the amount of soil leaching must determine to a large extent the balance of available nutrients. In other words, other factors being equal, the 800 millimeter isohyet must be at or close to optimal from the standpoint of human livability and survivability.
Apologize, we're 1 minute late, but that's fine. We started 1 minute late there anyway.